All right, we are carrying on with the final part of elements of programming. Done your first program, built-in types, data types, conditionals and loops, arrays, input and output. Now the last one is a brief case study called PageRank. So let's have a look. So communicating across the web has become an integral part of everyday life. The communication is enabled in part by scientific studies of the structure of the web. We consider a simple model known as a random surfer model. Consider the web to be a fixed set of pages, with each page containing a fixed set of hyperlinks, each link a reference to some other page. We study what happens to a person, the random surfer, who randomly moves from page to page, either by typing a page name in the address bar or by clicking a link on the current page. So pages and links in and out to different pages that people go to. The model. The first step in studying the random surfer model is to formulate it more precisely. The crux of the matter is to specify what it means to randomly move from page to page. The following intuitive 90-10 rule captures both methods of moving to a new page. Assume that 90% of the time the random surfer clicks a random link on the current page, each link chosen with equal probability. The 10% of the time the surfer goes directly into a random page, all pages on the web chosen with equal probability. You can immediately see that the model has flaws because you know from your own experience that the behavior of a real web server is not quite so simple. No one chooses links or pages with equal probability. There's no real potential to surf directly each page on the web. 90-10 or fixed breakdown is just a guess. It does not take the back button or bookmarks into account, and we can only afford to work with small sample of the web. Despite these flaws, the model is sufficiently rich that computer scientists have learned a great deal about properties of the web by studying it. To appreciate the model, consider the small example above. Which page do you think the random server is most likely to visit? Here we go. That's the model. Input format. So we assume that there are n web pages numbered from 0 to n-1, and we represent links with ordered pairs of such numbers. The first specifying the page containing the link, and the second specifying the page to which it refers. Given these conventions, the straightforward input format for the random surfer problem is the input stream consisting of an integer, the value n, followed by a sequence of pairs of integers, the representations of all the links. So this is an example, and this is found in the text files shown here as well. So again, so we assume that there are n pages. Here are the n pages, numbered from 0 to n-1, and we represent links with ordered pairs of such numbers. The first specifying this page containing a link, and the second specifying the page to which it refers. So here's a very simple example of the pairs of pages and the links. So these are the links, and these are the n web pages, and these are the links. Transition matrix. We use two-dimensional matrix that refer to as a transition matrix. To completely specify the behavior of a random surfer, with n web pages, we define n matrix such that the entry in row I and column J is a probability that the random surfer moves to page J when on page I. The program's transition is a filter that converts the list of links, a representation of a web model, into a transition matrix representation. Let's first have a look at, okay, this is the small file. This is a big file representing links that are chosen. These are the various links. This is the transition matrix, which reads links from a standard input and writes the corresponding transition matrix to standard output. First process the input to count the outlinks for each page, then apply the 90-10 rule to compute the transition matrix, assuming that there are pages that have no outlinks in the input. So this is also a diagram representing the input graph, how one page can look at different links. Input graph, and this is translated into a matrix, various degrees of the matrix, leap probability, which is fixed, link probability, and then you'll get transition matrix computation. So this is the actual program, random surfer. The program random surfer simulates the behavior of the random surfer. It reads a transition matrix and surfs according to the rules, starting at page 0, taking the number of moves as a command line argument, counts the number of times that the surfer visits each page. Dividing that count by the number of moves yields an estimate of the probability that a random surfer winds up on the page. This probability is known as a page's rank. One random move. Let's have a quick look at the code. So this accepts an integer, moves as commanded argument, read a transition matrix from send input, performs moves as prescribed by the transition matrix, and write to standard output relative frequency of hitting each page. So one random move. The key to the computation is a random move, which is specified by the transition matrix. Each row represents a discrete probability distribution. The entries fully specify the behavior of the random surfer's next move, giving the probability of surfing to each page. So here's the example that they're representing to generate a random integer from discrete distribution for each page and the probabilities for each one. Markov chains. The random process that describes a surface behavior is known as Markov chain. Markov chains are widely applicable, well studied, and have many remarkable and useful properties. For example, a basic limit theorem for Markov chains says that our surfer could start anywhere, because the probability is that a random surfer eventually winds up on any particular page is the same for all starting pages. No matter where the surfer starts, the process eventually stabilizes to a point where further surfing provides no further information. The phenomenon is known as mixing. Page ranks. The random surfer simulation is straightforward. It loops for the indicated number of moves, randomly surfing through the graph. Because of the mixing phenomenon, increasing the number of iterations gives increasingly accurate estimates of the probability that the surfer lands on each page, i.e. the page rank. Accurate page rank estimates for the web are available in practice for many reasons. First, using them to put in order the pages that match the search criteria, or web searches prove to be vastly more in line with the people's expectations than previous methods. So in terms of visualizing the histogram with standard draw, it is easy to create a visual representation that can give you a feeling for how the random surfer visit frequencies converge to page ranks. If you click on this page here, using standard draw, we can visualize how the random surfer moves through this for loop, and then eventually visualizing it as a histogram with page ranks. So mixing a Markov chain is directly simulating the behavior for a random surfer to understand the structure of the web is appealing, but can be too time-consuming. Fortunately, we can compute the same quantity more efficiently by using linear algebra. So squaring a Markov chain. What is the probability that the random surfer will move from page I to J in 2 moves? The first move goes to an intermediate page K. So we calculate the probability of moving from I to K, and then from K to J, or possible K, and add up the results. This calculation is one that we have seen before, i.e. matrix manipulation. Here's the diagram showing how that is done. The Powell method. We might then calculate the probabilities for 3 moves by multiplying the matrix P, and for 4 moves by multiplying P yet again, and so forth. However, matrix multiplication is expensive, and we're actually interested in a vector matrix calculation. So I have the various ranks for the pages, or showing the first move, second move, third move, 20th move, the matrix, and then the new ranks that can be calculated from it. Program Markov.py, let's have a look, is implementation that you can use to check convergence for our example. For instance, it gets the same results, the page ranks accurate to 2 decimal places, as shown here, but with just 20 vector matrix multiplications. So here's the Markov.py file showing the code to create the different matrix vector multiplications and writes each page rank to standard output. So I'm not going to run through this code. You can do this yourself because it can become quite technical. This is more of a intro video walkthrough, so I'm not going to delve too much into this code, but let's look at the lessons. Developing a full understanding of the random surfer model is beyond the scope of this book site. Indeed, it is. Instead, our purpose is to show you an application that involves writing a bit more code than short programs that we have been using to teach specific concepts. What specific lessons can we learn from this case study? Well, we already have a full computation model, primitive data types and strings, conditionals and loops, arrays, standard input output, enable you to address interesting problems of all sorts. Data-driven code is prevalent. The concept of using standard input and output streams and saving data in a file is a powerful one. Accuracy can be elusive. It is a mistake to assume that a program produces accurate answers simply because it can write numbers to many decimal places of precision. Often the most difficult challenge that we face is ensuring that we have accurate answers. Efficiency matters. There's also a mistake to assume that your computer is so fast it can do any computation. Power method is a far more efficient way than direct simulation to determine the page ranks, but it's still too slow for a huge matrix corresponding to all the pages on the web. That computation is enabled by better data structures and linear algebra. Cool, that's actually the end of section 1. If you want me to do the examples, please let me know. Exercises and Q&A, let me know in the comments. If you want me to go through this in detail, leave comments below for this video, and I'll do that. And now we are finished with section 1. We will be moving on to section 2 in the next video. Thank you very much. Hopefully you learned something.